Welcome. In this video I'll discuss implicit time integration methods. These are a kind of method used to solve systems in time where we have a very large range of timescales. And these are sometimes called stiff systems, although the definition is fairly vague and varies between authors. But essentially it means that we have a long timescale we want to solve. So it might be the evolution of an equilibrium on transport timescales, but there are some very small timescales like fast alpha waves, so setting the radial force balance, for example, in a tokamak. And these very fast waves, we don't necessarily care about following all the details of these waves. We just want to evolve past them while treating them as accurately as we can, but not necessarily caring about all the details of their evolution. So we want to try and step over these small timescales while solving for very large timescales. As we'll see, there are trade-offs, and this isn't really a perfect system. So there's always some approximations you need to make when you do this, and particularly you tend to damp any waves that you don't resolve. It's one of the trade-offs you make. But I'll show you some examples of how this method works for simple cases, and then discuss a bit how it extends to more complicated cases. And then at the end, a bit about semi-implicit and so-called implicit explicit methods. These are IMEX schemes, which are, at least in principle, fairly similar in what they try to achieve. So the aim of implicit methods is to overcome time step limitations. So example processes, I say, are fast waves, where we might want to step over them, or heat conduction is another process that typically limits the time step, because this is extremely fast in high temperature plasmas, and so this can be a limiting factor in the time step. And so we want to try and overcome this by using an implicit scheme. Now there's a few simple examples we'll start with. Just about the simplest one we have is a damping wave. So it's a single variable. We're just solving this equation for dy by dt is just minus 10 times y. So it's a very simple system, but it shows some of the basic ideas. And so this is time, this is y. We start at t equals 0, y has some value, let's call it a, and decays exponentially. And so we just have the solution that y is just a e to the minus 10 times t. And so the solution is fairly straightforward. What we'll see is if we use standard time integration methods, this can look very different. And so many methods are so-called explicit, which means that we solve this equation so that we can calculate this at a given time, and then just update the next time without having to invert a matrix or do any kind of complicated solving of nonlinear equations, or inverting a linear equation. These are called explicit schemes. The simplest explicit scheme is an Euler method, but this also includes things like RK4 and Adams sort of multi-step methods as well. So an example, if we try and solve this with an explicit scheme, so for example Euler's method. So it's an explicit scheme, so that although this is the simplest method, the same restriction or very similar restriction will apply to other methods. And all this is we do a difference to work out this derivative. So we say that this is the next time step minus the current one divided by the difference in time. So it's just a simple approximation to the time derivative. And in an explicit scheme, this depends on the value of y at the current time step. So it's just minus 10 y n. And we can then rearrange this equation because it's a simple function of one variable. We can just write this yn plus 1 is just yn. And then here we have this factor here, so we have a minus 10 times delta t. So we have here, I'll just write this 1 minus 10 delta t factor there. And so this is the explicit method. So every time step we take the value of y and we multiply it by this factor. And you see that if, so firstly, if delta t is equal to 0.1, then this goes to 0. And so it immediately goes to 0. Get that yn plus 1 equals 0. So that's this first case So this will be basically, we'll just do like this and go to 0. Like that. If we make a 0.2 example, this makes this this -2, and so this whole thing just becomes -1. So yn plus 1 is just -yn. And what's happening here is if we have a -2 equation where it essentially reverses sign and just oscillates. So that's this case here. And then if it's bigger than 0.2, then the magnitude of this becomes larger than 1. And in that case, the magnitude of yn plus 1 is bigger than the magnitude of yn, although it will also change sign, but this will be unstable. So there's a limit beyond 0.2 where the whole thing becomes unstable, and beyond 0.1 the sign of y changes, so it goes from positive to negative back to positive. So 0.1 is essentially a limit beyond which we start to get negative y's when we shouldn't do. The solution should only have positive y. So this gives a time step restriction. So either less than 0.2 for stability or less than 0.1 for positivity, so being positive. So then if we try modifying this, so try an implicit method. So the simplest implicit method is the backwards Euler. So we're going to call it backward Euler. And it's very similar to the forwards Euler, so the standard Euler method that we showed here. I'll just write this out here, so it's the same so far. So there's the same final difference for the time derivative, and then on the right hand side, the only difference is that we make this now a function of the next value of y. So in this case it's quite easy because the function on the right hand side is quite simple. In general, the right hand side can be a nonlinear function of y, and y could be many different variables. And so this in general is more difficult to solve. In this case it's quite simple. We just again group everything, all the y plus 1s on left hand side, and so we just have that y plus 1, they have 1, so I'm going to multiply through by dt. So we have 1 plus 10 delta t, so I've just moved this here, then moved over to the other side. And that is equal to, the only thing that's left over is this yn. And so we have the solution, or the iteration each time step is just, this is yn, 10 delta t. And so you can see now that this is always bigger than 0, sorry, not 1, bigger than 0. So it doesn't matter how big we make delta t, yn plus 1 will always be positive, and so we don't get this oscillating behavior that the explicit method had, and there's also no limit to how large delta t can become. So it's always stable. Y always decreases. It gets less and less accurate as delta t increases. So as delta t increases, the decay rate will be worse, further from what it should be. Essentially, you end up with, this is time, this is y. This is the exact analytic solution. What you'll end up with is if delta t is quite large, that actually won't decay fast enough, so you'll get decays which are too slow. So as you make delta t bigger and bigger, it will still decay, but just slower than it should do. So as delta t increases, it moves up and decays slower. Okay, but it's always stable, and this kind of methods which are stable for these simple systems are called A-stable. So for exponentially decaying systems, such as this damping equation here, if a method is stable for arbitrarily large time steps, then it's called astable, and many implicit methods are. There are also more useful or more broad things like L-stable methods, which are stable for a wider class of problems, but astable is a pretty good start for most methods. Okay, so then we're going to look at what happens when you solve a wave kind of problem. So many problems in MHD and fluids involve waves or wave propagation. So I'm going to simplify this and just have an oscillating system. So we just have, we're going to have a full derivative here. So we're going to df by dt is g. So we're just going to have two variables, f and g, and we have dg by dt is minus f. So you see, by substituting this into there, the solution is just that f is some kind of f naught e to the I t. So there's a sort of oscillating solution for both, and g has a similar solution as well. So then we're going to do this with the backwards order as well. So what we're going to see is what happens when you make the time step large. So we have an oscillation which you could resolve and accurately, well, not very accurately with the backward method, Euler method, but you could in principle solve accurately. But what if you want to take large time steps? What's the penalty? And the result will just be that the wave gets damped. But I'll show you how this works. So it's backward Euler, so we can do the same. So this is fn plus 1 minus fn. So I'm just doing the first equation here. And this is just gn plus 1. And the second one is gn plus 1 minus gn over delta t as fn plus 1. So then we rearrange this equation, again multiplying through by delta t. And so we just have that fn plus 1 minus delta t times gn plus 1. So I'm putting everything with an n plus 1 on the left hand side, and everything with an n on the right hand side. So here we have a gn plus 1, and then here we have another, where's a minus sign? So here we should have a minus here. So plus delta t plus fn plus 1 is gn. And this of course is just a matrix equation, so it's a set of linear equations in this case. And so we can just write this whole thing in terms of a matrix. And here we're going to put fn plus 1, gn plus 1 here. So this first equation is fn plus 1, then we have a minus delta t for the gn plus 1, and that's equal to fn. It's going to be gn here. And then the second one is that we have delta t times fn plus 1, so we have delta t plus gn plus 1, which is this one. Okay. And of course we just invert this equation, and so we just end up with fn plus 1. So in this case we have two equations, so we have a 2 by 2 matrix. In general this is what happens with implicit methods, that if you have n variables, you end up with an n by n matrix to solve. And the number of variables can be, say, the number of grid cells times the number of quantities being solved. So this can be millions, can be a billion, for example, as in a large simulation. This can be a very large number of variables, and so you end up with a huge matrix. Fortunately, most of the time, most of these elements in the matrix are 0, so it's a very sparse matrix. But in general, you can't solve it like this directly. You use an iterative method to solve it instead. But here it's just 2 by 2, so we can just do like this. So 1 plus delta t squared from the determinant of this. And then we have again like this, 1 delta t, this becomes a minus delta t and a 1. So it's just inverting that. And then it's just gn. So, okay, so it's worth having a look at what this means. So if you multiply out these equations, so this matrix here, for example, this part here, this is the same as the forward Euler method, because this just says that fn plus 1 is fn plus delta t times gn, and the same for gn plus 1 is just gn minus delta t times fn. So this is basically the forward Euler. And then here we have this damping factor. So it goes like delta t squared, so it's larger than any of these terms here. And so as delta t goes large, so as delta t goes to infinity, for example, this term at the front damps the whole thing towards 0. And so as the delta t gets larger and larger, this oscillation decays in time. And so the solution is something like this, that you'd have if this was time, as we say f, so some kind of oscillating wave like this. As we make the oscillations larger, what happens, this reduces the frequency, so the frequency is reduced by this factor 2, and so the wave is slightly slower and also decaying in amplitude. So what we find is that the wave kind of decays like this. So it has a slower frequency and it also decays in time. And this is generally true for unresolved waves and oscillations here, but in general for waves. In implicit methods, is that they tend to have a lower frequency and decay in time relative to the explicit or resolved waves. So unfortunately there's no such thing as a free lunch, so implicit methods are good in that they can take large time steps, and in some cases this means they can be much more efficient than explicit methods, but there is a price that there are waves which will not be resolved correctly and which will be damped by these methods. But in general, they work pretty well, and in many cases for plasma applications, because there's such a wide range of timescales, they can work extremely well. Okay, so very quick, just look at other extensions, so different methods. There are, for example, semi-implicit schemes and variation, sort of more modern variations on these called IMEX schemes. So IMEX, so implicit explicit, is a modern kind of variation on these. So the basic idea is that you have two kinds of waves, or two types of phenomena in your systems. One is the very fast timescales you want to step over, and one is the very slow timescales you want to resolve. So you separate your system into these kind of fast processes, which you don't really want to resolve, so you're quite happy to step over them, and then slow processes which you want to resolve correctly, and so you don't want to damp these processes, and so these ones you can basically solve implicitly, because you're quite happy to step over those timescales, and these ones you can solve explicitly. And they all essentially have a variation that you split your system into sets of equations. So you might have some set of equations y, which might be a big vector of millions of variables, for example, and it's some combination of two functions. So you have two functions f and g, for example, which might be nonlinear, but one of them is say fast. Let's say is the fast one, and that's say slow, and then what you do is you essentially treat this fast one implicitly and the slow one explicitly. So the backwards order you might do this kind of thing, where you have essentially the backwards order method there, and then you have f y n plus 1, and then here you'd have just g of yn. So you can rearrange this equation, and now you're just solving for this f part. So we have a yn, then we have a minus delta t times f yn plus 1. And then on the right hand side, just have a yn plus delta t times g. So the advantage here is that if g is quite complicated, so g might be very nonlinear, or have, for example, if it's hyperbolic, these might have very strong limiters, for example, which makes it very difficult to invert them, then this you can just calculate very simply, because you know yn already. So this part is easy to calculate. And then if this is the fast part, then you need to solve this kind of nonlinear problem here. So in general, this can be nonlinear. And so some kind of a Newton iteration, for example, is quite common. Newton iterations, or partially linearizing the scheme. So there are things like predictor corrective methods where you kind of linearize this, or you make some approximation, and then you correct the solution. So things like Newton predictor corrector, or things like even Picard iteration can be used in some cases for this. So this is a nonlinear problem, but it's one way of splitting up your system into fast and slow timescales, and then ideally putting very nonlinear terms in here to make this part easier to solve. And these can, in many cases, be a good compromise between implicit and explicit schemes.